Good afternoon, everyone. I'm going to get started so I can get you folks out in time for lunch. So my talk is about the NIM programming language. So what is the NIM programming language? So here's just a laundry list of things that it is. It is a typed imperative language. Oh, hold on, forgot my speaker notes. It is a typed imperative language, and it's sort of this n-way love child between like Ada, Modula, Oberon, Pascal, and Lisp. And it compiles to like C, C++, and JavaScript. So it's got like a nice macro story. It's got a world-class static introspection story. I'm going to get a lot more into that later. It's got a minimal runtime because it also does static resource management. Think of it as more like compile time RAII, C++ style. And it also has world-class C and C++ interop. And yes, I mean C++ interop. Like, you know, template-heavy C++ interop. So I'm going to show you that as well. Oh, let me go full screen on that. So now that was the what. This is the why. Why should you care about this language? First of all, it looks familiar. Like, you know, the syntactic familiarity is a cheap marketing trick, but it looks enough like Python that I'm just going to like throw out a bunch of code at you folks, and I'm betting that most of you are just going to pick it up in context. So I don't have to teach you anything about this language. And also, more importantly, it is a very fast compiler. The compiler, the standard library, and the package manager build from C sources. They bootstrap in about 6 minutes flat on this dinky ThinkPad, this little 5-year-old ThinkPad. So I can stick a debug statement deep inside the compiler, and I can see that debug statement in my app code in about 10 seconds. A major NIM project, the LSP server for NIM, that uses the compiler as an API, builds from scratch in about a minute. Forget all of the other features aside, if you don't have fast user feedback, none of it matters. I can't really demo fast user feedback, but I think it's important enough to be like one of the most important things about NIM. The second big thing I want to talk about is static introspection. This is the ability to treat your compile time environment as metadata that you can query. I'm going to say that this is a superpower that NIM has. In most other languages, types and all other metadata are locked in and impossible to access in a programmatic way. What fields does this record have at compile time? What are they? What are their types? What is the type of an arbitrary expression? And we'll see more examples of that in a second. The third big reason why I think you should care is interop, specifically with C++. The key to adoption is interop. TypeScript, Scala, F#, all three of them, nice languages. But because they have great interop with JavaScript, the JVM, and the CLR, they are now important languages. You wouldn't look at them twice if they didn't have that. And specifically C++, because C++ has a ton of useful, important, and critical software written in it that takes a huge amount of effort to access. Things like Qt, the GUI framework, TensorFlow. Many shops cannot get out of C++ because nothing else can talk to it, at least not without significant effort. Imagine zero overhead bindings to template-heavy APIs. But first, I want to show you a couple of demos just to show you how easy it is to get started with this language. Here, I'm going to have a little web server example that takes the URL path and capitalizes it. OK, so here we go. By the way, if you can't see that code, please scoot up. So I have some imports. And here I have a handler for the request that's coming in on this web server. It's called handle. It's a procedure that's called handle. It takes a request and outputs a feature. None of that really matters, except now we can get it, you know, it hands you back a 200 and a message. So I can take that request and I go r.url.path.split file. So this is getting the path out of that URL. Split file splits it into its various components. .name, to, like that. And just for grins, we can go ahead and stick this in a JSON blob. Okay? And now let's start it on port 8000. Alrighty, so let's run that. Switch to our terminal. And it returned that JSON blob. So thrill, have some JSON. Yeah, thank you. So what I'm hoping is, What I'm hoping is that you agree that this looks like code that you've seen before. Even if I explain nothing about the language to you, you could sort of like work your way through this and figure out what it's doing. Nothing too surprising here. On the other end, I want to talk about manual memory management, allocating a bunch of strings and then freeing them. So here we have our first type in NIM. It's just an object, and inside of that object is a C string. A C string is nothing more than a pointer to a bunch of characters, a bunch of null terminated characters. Okay, so then we have a function that does something with that. So it takes a number, and that's the number of strings you have in that array, and it allocates enough space for it. And it goes ahead and creates that string and allocates some space for that. And copies it into place. This is exactly what you would do in C. No difference. And then we can make a bunch of those things. So here I'm making 10 strings. And I can run through them, and for each one, I print it out, and then I deallocate it at the same time. And then I actually have to deallocate the array as well, like so. So when I run that, it's printing out all of these strings. And when I val grind it, it's val grind clean. There's much better ways of doing memory management in NIM. But if you need that kind of access, you have it. Okay. So what I was hoping to show you is that you can do it. You can learn NIM. It's not that hard. The language has a lot of power and a lot of like really cool and weird constructs, and I'll get to those in a sec. But for the most part, you don't have to like sort of change the way you think about programming just to stuff a JSON blob in a web response. Right? So without really thinking too hard, you can write code that is about twice as slow as C, which is pretty good for the most part. It has an extensive and diverse standard library. Every demo I'm going to show you is either going to be using the language built in or something in the standard library. No package managers involved. And all of the code is sort of this bog standard imperative thing that is pretty familiar looking, even inside of the standard library. Okay, so on to the fun stuff. Oh wait, before I do that, I want to call out this really cool syntactic feature that NIM has. It's called Uniform Function Call Syntax, UFCS. And the way it works is really simple. So say you have a function, right? It takes a bunch of arguments. You've got f takes arg1, arg2, and arg3. So the normal way you would call this function is you would go f and then open paren arg1, arg2, arg3. You've seen this before. What UFCS allows you to do is go arg1 dot f open paren arg2, arg3. So if this looks weird, it shouldn't because we've already seen this. So when I was doing that server example, that r.url.path.splitfile, all of this stuff, here, splitfile and 2 upper ASCII are just plain old functions that happen to take a path and a string as their first arguments. So UFCS allows us to just chain those things along. So you just have plain old functions. There's no need for a language construct that attaches some kind of like implicit dictionary to an object. like vtables or type classes. Just work with functions. And this is what Tomas Petracek of the University of Kent calls dot-driven development. He has a really cool paper called Data Exploration Through Dot-Driven Development. And this is the idea that you can explore an API just by going thing, dot, thing, dot, thing, dot, thing, all the way down. He's got a whole paper on this. So your IDE can really help you explore the environment when you have that kind of facility. And although NIM doesn't go as far as F# with that, I think UFCS is very much within the spirit of that. And it's a very simple syntactic transformation. Very easy to do in the compiler. And has a lot of consequences. Punches way above its weight class, in my opinion. Okay, so cool. On to the fun stuff. So what is static introspection? Static introspection means that most of the NIM programming language is available to you at compile time. So here in the static block, I have an echo hello world. What that means is when I compile this, the compiler spits out the string hello world. And most of the standard library is also available. So in this static block, I am mapping over this hello world list and capitalizing everything. So map and to upper ASCII, these are standard library functions. And it prints out hello world in caps. So the way that does this is not magic. I mean, so how it does this is in addition to having a C backend, there's also this like register-based interpreter backend that understands some subset of the language. And the compile time constructs are run inside of that interpreter. There's no magic here. You can also ask whether some arbitrary expression compiles at compile time. So this is asking the question, does the expression 1 plus 1.0 even compile? And spit that out at compile time. Does the expression 1 plus hello world compile? Spit that out at compile time. So it's spitting out true and false, respectively. And it works with inside of your current type environment. So here I have a type, which is a tuple. By the way, tuple in NIM doesn't mean what tuple means in literally every other language in the universe. I don't know why people do this. But a tuple in NIM is just an anonymous map. It's just an anonymous record. So this is a record that has an I field and an S field of type int and string. So at compile time, I'm instantiating that with 1 and blah. And I'm asking, hey, does O.S.2 upper ASCII compile? So it understands that there's this like type in the environment, like this O type, and it says true. You can also get the type of something directly. So at compile time, this is asking what is the type of this arbitrary expression? And it will split out float because it's get coerced to float when you add. And you can use that in place of a type. This isn't just a string. So here I have a function f that takes an int, I, and I have a let here, x, and here the let is compile time reflecting on the type of the argument that was passed in, and using that as a stand-in for a type annotation. So this is exactly like saying let x colon int, except I'm reflecting instead. And I also want to convince you that the types are calculated, not extracted. So there isn't some cheesy thing where it goes through the AST and finds a type signature and grabs that part of the type signature and hands it off to you or something like that. No, this is actually calculated. So here in this type of, I have a block. A block is just an anonymous scope. And I have a function. I have an identity function. So that capital T is a generic parameter. So it's taking that generic parameter and just spitting it back out. So when I call identity on to upper ASCII blah, at compile time, it is calculating that the type of that expression is string. So what do we do with all this? So imagine you're at a job interview, and they say, Fizzbuzz. And you're like, yes, sure, I can do that. And the interviewer goes, that's great. But can you make it faster? And you're like, when do I start? Because for folks of you that can't see in the back, adding that compile time pragma to a function makes it so it runs at compile time, so all of that Fizzbuzz stuff is happening at compile time. So it's faster than doing it at runtime, and you get the job. Okay, that was cheap. That was really cheap. I'm sorry. That's almost beneath me, almost. So anyway, a more serious use case is a problem that I've encountered in every job that I've done so far. This is the idea that you have a type, but you need to migrate that type over time as things change. You need to diff types and migrate them. So here's an example. Say you're greenfielding a project, right? And you need to model a person. And you're trying to do it in the quickest way possible. So you have a first name, a last name, and an age. OK, cool. And then time passes. And then you add a middle name. And you add an address. And then more time passes, and we're up to today. We've gotten a little more precise with our types. Our age is now a natural number. And our address is now this sort of more structured thing that has like a street and a city and all of this stuff. All right, beautiful. What is your migration story? How do you get from that first initial type to the second thing with the middle name and the address to the third thing with the more refined types? First of all, why should you care about this? You're saying, hey, I have a web client. I can force an upgrade on clients. It doesn't matter. So what if, at some point in the past, you provided a sort of a curl upload download feature for your REST API that allowed them to upload and download like person data, right? Why did you do this? Because some customer who's paying you a lot of money decided they would rather work with your person data in Excel than in a web GUI. And they're not wrong. Nothing wrong with that. So now that customer takes an upgrade, they try and upload a CSV from an old version, and it breaks. This happens all the time. I suspect it happens in a bunch of your code bases as well. So what do? The first thing we can do is embrace the boilerplate. Keep copies of the old types around, right? Manually write that tedious code that passes common fields through from version 1 to version 2 to version n. From experience, I know that this approach is unsustainable, and more importantly, it's false simplicity. This quickly becomes one of the worst parts of your code base. No one wants to work on this because it's soul-sucking and it's tedious. Your backlog fills up with migration tickets. We in the business call those good first issues for people onboarding. Or, let's say you have a language that, shall we say, has an expressive type system. Then you bring in an expert who writes a framework that's 5 layers of abstraction above the term level, right? And now you've traded the problem of no one wants to work on a migration to no one can, or like that one person can. And at this point, you start having these intrusive thoughts, like maybe I should have just used a dynamic programming language, you know? Or static introspection, thrill of this demo. Okay, so here we have something that looks like that first type that I talked about with the first name and a last name, and the version 1 of that with the first name and middle name and an address. So I wrote a macro that diffs those 2 types at compile time. So it pulls apart the first type, it pulls apart the second type, and it hands you back a type that is the difference between those 2 things. So how does this work? So let's run this. And that's what it's handing you. It's handing you back an anonymous tuple. This is a type, by the way, not a runtime value. An anonymous tuple with 2 fields, a middle name and an address, both of which are type string. Now, let's gen up some data. We've got a person, first name, last name. OK, now you can write a migrator. And this migrator compile time reflects on that diff type, on the difference between those 2 types, which is a tuple of a middle name and an address. And it has to provide default values for those 2 things. Okay, cool. Now, I wrote another macro called migrate that takes some data, that original P, namey McNameface, and a type that you want to migrate it to. You want to migrate it to version 1, and a migrator, and combines the two things together. So when I echo it, that's what I get. I get the first name, but I also get the middle name, and I also get the address. Okay, so let's make things a little more interesting. And here we have a second type. So this is sort of looks like the more refined type from today. We have an address, and the address is more structured type, which has like a street, a city, and all of that stuff. So what does a diff type for that look like? So let's run that. And now we have something a little more interesting. Because now you can't just fill in a default value. Because think about what we had. Before we had an address that was of type string. Now we have an address that is of type address. So you can't, when you migrate this thing, this macro is smart enough to go, okay, you can't just give me a default value. You have to give me a transformation. That's a function. That's an anonymous function that takes the old value and spits out something of the new value. And so you get started writing your migration. So I have a person2 migrate that reflects on that diff type between version 1 and version 2. And now I have to write a function that does that migration. And it fills in the address with this will suck, and it will. Like, I hope you're never in the position of having to take an arbitrary string and parse out a legitimate address from that ever. Ever. Like, break out your parser combinator libraries or regular expression libraries. Like, but in any case, if you want to keep your migration honest, you have to do this. So when I run this, and here I migrate from person 1 to person version 2 and all of this stuff. So when I run this, now I get the first name, the last name, and the address. So here we have a principal migration from one step to another. So if somebody ever uploads a CSV from an old version, they can always be migrated to the new version in some way. So I think that the takeaway here is that if you have a great serialization, deserialization story, but no migration story, you have at best solved half the problem. And also, being able to print and take apart and reassemble like static structures is absolutely critical. And most type code, in my opinion, is more complex than it needs to be because it does not have a static introspection story. And thirdly, it's just fun. You're doing this like Brett Victor style direct manipulation of static constructs. And that's just cool. So now I want to talk about static resource management. So first, let's, as always, make a type. So in this case, by the way, a lot of these will mirror that first thing that I showed you where we were just putting a bunch of strings inside of a list. So here I have an object that wraps a sequence of strings. This is just native NIM code. There's nothing wonky going on here. There's no allocation. There's no like pointers to characters or anything like that. This is just native NIM. And we have a function that does something with it. So this function make O takes an int, and it just kind of uses a for loop to add a bunch of strings to that sequence and spits it back out. And then we have a function that can print it. This one just makes one of those O objects and iterates through it with a for loop and prints it out. Very simple, like bog standard stuff. And we have a main function that can run all this stuff. So when I run this, I didn't mean to do that yet. That was a secret. I should not have showed you that yet. So when I run this, it's printing out, it's running all the stuff. It's just printing out, string indexes from 0 to 9. Now, if I val grind this, it's val grinding clean, right? There's no leftover memory. So somewhere in here, nim is implicitly cleaning up after itself. So where is that happening? Well, nim has what's called a destructor hook. This is a destroy hook. This is just like a destructor in C++. And you can override it. And this is how you do that. This equals destroy is a special function in nim that means like destroy the argument that that it's parameterized with. So here all I'm doing is saying destroy the thing, but debug something to standard out first. So when I run this, so now after the last use here, where it prints, it's destroying it. Before the after. Yeah. Right? So let's see what happens now if we return. Instead of just printing it out, we also return it. And we print out the strings inside of it. When we run that, we see that destruction doesn't happen until the last use. So somewhere in there, nim is statically like tracking all of these resources and figuring things out. So nim statically injects destructors after its last statically tracked use. It's like RAII in C++, but it's completely unobtrusive. You can just kind of forget that this thing exists. Also, somewhat surprising that most people don't know about, is that nim has basic rudimentary linear types. This isn't advertised anywhere in the manual, but it actually does. And I think it illustrates some key philosophies in nim design. Let me show you that. So back to our string array example. Okay. So let's make a print function that has a sync. Sync indicates that this is a linear type that is consumed by this function. What that means is that if you call print sync with some object O, that object O is now consumed and statically not available for use anywhere else. So what this means is that this is saying that you can only use O once. Or actually, it's an affine type. You have to use it at most once, not exactly once. So what we can do is we can say make O here, and then we can call print sync on that O and see what happens. OK, let's run this. OK, what's wrong? Who sees what's wrong? Anybody? Huh?
It's destroyed twice.
Yes, sir. Well done. It's destroyed twice. So it's destroyed after the first time it's printing, and it's destroying again after the second time. If I val grind this, oops, I got to parameterize it with something. Look at how much more memory it's using. It's almost double. Something's going on. So at this point, you're like, oh, I guess linear types are just broken in them. Like, this feature sucks, right? Yeah?
Sorry, can you define what you mean by linear type?
Are you asking what is a linear type?
Yeah.
So a linear type is a type that a linear type is a type that can only be used once, or it has to be used exactly once. So this is actually an affine type, which means it has to be used at most once. That means it shouldn't be available after you use it once, yes?
And it's similar to Rust's concept of ownership. So a sync means that this is an owned value.
Okay, cool. So I could tell you the answer to this. I know the answer to this. But I'd rather just show you. And this, I think, illustrates something cool about nim. So nim has this command line argument called expand arc that statically shows you what the intermediate code looks like after all of the destructors and copies have been added to it. after it statically tracked all this stuff and added that stuff. This is valid NIM code. This is what the compiler sees. And the problem is right there. So NIM goes, okay, cool. I know that I'm supposed to consume this. You've used it after I've consumed it. I'm just going to go copy it. This is deliberate. This is a deliberate design decision. And what it illustrates, in my opinion, is one of the first philosophies of NIM is to get out of the user's way. When there is a choice between copying and bugging the user with some kind of error, NIM just goes ahead and copies. Think about the far-reaching consequences that has for the standard library and all of NIM code. You can just write NIM code and forget about the fact that it's doing the stuff behind the scenes for you. It's not bugging you with an error. It's just letting you write code. And the second big thing is this philosophy of show, don't tell, or that's what expand arc does. Expand arc is showing you exactly what the compiler sees. And people have used that facility to spot bugs in the compiler itself. That's far more powerful and better than some error message, in my opinion. So, by the way, we have control over this. What we can do is we can disable copying. And the way you do that is just attaching an error pragma to the copy hook. And when you do that, now you get an honest-to-goodness error that says there's no copy available for this type because there's another read on line 35, and if I go to line 35, that points to the last thing. So now we've recovered the behavior that we want, if that's the behavior that we want. So static resource management in NIM, it works well. All of the standard library and most NIM packages have moved to it, and they get a nice little speed boost from it. And the idea is just relax. Just write some code. Most of the time, it'll be fine. When you need it, profile and then optimize. And you have complete control over whether copies happen, how destruction happens, how a bunch of stuff happens. But for the most part, you don't have to think about it. So for my last little piece, I want to talk about C++ Interop. And I'm going to show you how to reuse the standard template library of C++. And here, we're going to add a bunch of strings to std vector. Std vector is a standard C++ thing. So here we go. So the first thing we do is figure out how to map a NIM type to a C++ type. This is pretty cool. So you have a NIM type called std vector. It's parameterized on some generic t. This maps at codegen time to this string, std vector, with this quote 0 inside of those angle brackets. And what the quote 0 does is grab that generic argument and just splice it in place. So if you want std vector, angle bracket, std unique pointer, whatever, the thing inside of that thing that you parameterize it with is just spliced into place. So we have a std vector, we have a unique pointer also similarly parameterized, and we have a std string. That's all it takes to map a NIM type to a C++ type. And then we can define some operations on the vector. So here we have a vector constructor. And the vector constructor similarly takes that quote 0. It just splices in that argument. And it's an empty constructor because we're initializing an empty vector. And then we use the mplaceBack function from the C++ standard template library, and we add the thing that we're passing in. So this pretty much sort of compiles to something that looks like that t that you passed in over here. The at means the rest of the arguments inside of that function. And you can use getIndex. And here it's using a different piece of syntax. Those hashes refer to, respectively, the first and second arguments passed in. So this actually code gens something that looks like v5 or whatever IDX that you passed in over here. Something like that. So we have similar things that we can do with a unique pointer and a std pointer. So now we can do some cool stuff with this. We can make a function. Oops, I didn't mean to do that. We can make a function that uses all this. So this function takes in a num, it's an int, how many strings am I allocating, and it produces a std vector of a std pointer of a std string, all in nim types. So here we make a vector, and then we just iterate through that. We just use a for loop and create a C string and add it using the functions that we just created. So let's make like 10 of these things. I guess that should be num. Oops, whatever. And let's run through them. So here, it's using nim functions, getting the vector, getting the index, getting the inner thing inside of that unique pointer, and then getting the string out of the std string. And when I run this, it should just print out string at index 0 through 9. And we don't have to worry about memory here, because the C++ standard template library, vectors and unique pointers take care of themselves. Their destructors destruct the thing that they point to. So if I run this through valgrind, it should valgrind clean. That's actually a fair number of allocations. Not sure why it does that. But it's clean. Cool. And the last thing I wanted to show you, I guess I have time for this. Last thing I wanted to show you is this thing's really cool. This is a factorial at compile time. Okay, so this is just a fun example of the kind of interop that you can do between nim and C++. So here, by the way, this is an emit pragma, and emit pragma in nim means that just take whatever's inside of those curly braces and just splice it into code gen, right there. So this, all of this C++ gets just gets bolted in right there. And what the C++ is doing is it's using this recursive template trick. So this is an old trick. You can find it on Wikipedia and all this. This was one of the first examples that they found that C++ templates are actually Turing complete. And the world has never been the same ever since. People do crazy stuff with C++ templates now. Yeah. Yeah, it's nuts. But okay, so what this does is it inlines, so if you parameterize it with the static string and a static number 5, it will inline 5 times 4 times 3 times 2 times 1. And the compiler will sort of golf that into a constant. So this is a compile time factorial in C++. Okay, cool. How do we use that from nim? Right? So that's what this is about. This is an old trick. The new trick is how we bind to this stuff. So here we have a type. This type is just like the std vector thing. It has this quote O thing over there. But instead of taking a T or an int or a string or whatever, it's taking a static int. This is like type level numbers and strings and things like that in Haskell if you're familiar with that kind of thing. Cool, so we can parameterize it with a number, 10 or 5 or what have you. And how do you get the value back out? Well, it uses this thing called a type desk. A type desk is a meta type. It is a type that witnesses another type. Right? So it's like how in Haskell we have a proxy where a term witnesses a type, and here we have a kind witnessing a type, this kind of thing. So if you don't know what that means, it doesn't matter. All that matters is you can carry a type level number inside of that construct and hand it off to C++. So when this code gets generated, it looks something like something like that, it looks something like that when it generates the code in the end. So here I can take factorial 3 plus factorial 3. Those will be calculated at compile time. And it gives me back 12. 3 times 2 times 1, plus 3 times 2 times 1. Anyway, so that was just a fun little party trick. So anywho, what C++ Interop does is now any C++ library is easily accessible from NIM. Your ecosystem just got orders of magnitude bigger. And trying out NIM in a C++ shop is now a low-risk gamble. It's not no risk, but it's very low. So to wrap up, first things first, a fast compiler changes the game. If you have two equal languages, one with a fast feedback and one with slow feedback, what you have are two different languages. And I think without that, all of this other stuff doesn't really mean all that much. I think that static introspection gives you the level of dynamism and flexibility that you get in very few other languages. And when you need it, nothing else will do. I can't think of a better way of doing that type migration stuff that I showed you earlier. I can think of worse ways of doing it, but I can't think of a better way. And you get all the benefits of static memory management, but it mostly gets out of your way and just lets you write code without worrying about it. But the control is there if you need it. And C++ Interop makes NIM a viable alternative in places where almost no other language would work. Plus, it increases the size of your ecosystem manyfold. Anyway, so that's my talk. Thank you for coming.